The universe. What a concept. A vast realm of undiscovered galaxies, unexplored worlds, unknown reaches. A thing so large, we really don't know how anything in it works. In today's episode, as in every episode, we expose the nature of the cosmos in our own backyard, simply by taking a look around you. Look around you.
Look around you.
Look
Look
around
around
you.
you.
Have you guessed what it is we're looking for?
That's right. Quantum mechanics.
Quantum mechanics. A phrase you've no doubt heard used in relation to a large amount of stuff you didn't quite understand. In this way, it is rather like a foreigner with a heavy accent, or a word you've repeated so many times it's lost all meaning. Now, unlike these things, quantum mechanics is based on the fundamental level of matter, that of the atom. But what is an atom? Well, atoms are the smallest particles we know about, aside from all of the smaller ones, and they make up almost all matter in the universe. It was also the name of my journalism professor, Adam Tischler. You know, I never wanted to be a scientist. I wanted to be a journalist. Well, ever since I stopped wanting to be an astronaut, I wanted to be a journalist. Something adventurous, you know, sailing around, getting news stories. Not sitting in a lab all day, writing down point after point of useless information. Nobody even reads it, you know? I swear, it's all just a load of...
Right, so, anyway, atoms are very small. In fact, they are so small as to be invisible, which makes them very difficult to see. If the universe was the size of a porpoise, an atom would be so small it wouldn't even make sense. This sort of distance is called a Planck length, after Johann Planck. There are over 12 different varieties of atoms, each representing a separate element. For example, helium is commonly used in the production of balloons. Germanium is used in synthetic dyes, and lead is used in the peanut butter sandwich you just ate for lunch.
Each of the atoms is made of a nucleus, in turn made up of protons and neutrons tied together with string, and a series of electron shells. The vast majority of each atom is empty air, as the particles find each other offensive and try not to get too close.
The electrons, protons, and neutrons are, in turn, made up of many smaller particles. There are 2 photons in one proton, 7 volts in an electron and a proton in one nickel.
Photons are particularly interesting particles because they're not really particles at all. While it's true that under certain circumstances they behave like particles, under others they behave like waves. However, when examined under a microscope, they prove to be nothing less than small creatures that like to feed on plankton.
Although we've been using them in our eyes since time immemorial, the first known sighting of a photon was made by Franz Kepler in 1861, hidden in the extracellular matrix of a plant specimen. In 1864, Kepler named his little pet Pac-Man after his late mother, making the first video game and, in the process, placing his name forever in the annals of history.
Because photons are highly trainable creatures that act as both particles and waves, they give us unique insight into the realm of quantum mechanics. They also gave us our first hint at quantum uncertainty.
Up-and-coming genealogist Albert Einstein, later famous for his theory of relativity, was studying photons in his lab for no good reason when he discovered something peculiar.
If he informed a photon how fast it was going, it would suddenly become completely lost.
He subsequently discovered that if he then told one where it was, it lost all sense of velocity. Now, Einstein wrote this off as an enigma, but the late Dr. Bob Heisenberg
Extrapolated from this the Heisenberg uncertainty principle,
which basically states that it's impossible to know anything about anything on the quantum level without preventing yourself from being able to know anything else about it. I think.
Upon reading Heisenberg's paper, Schrödinger's cat hypothesized that an event with two possible outcomes will result in both simultaneously until examined, when one form will be assumed. To test this, Schrödinger placed his cat in a box with a vial of toxic gas, which might explode, killing the cat. Indeed, the hypothesis proved correct. The cat was both alive and dead at the same time. While in the box, the living form discovered the cure for cancer. But, alas, the cat assumed the dead form upon opening the box, and the cure remains a mystery.
Today we will be performing a modified version of this experiment, as PETA has confiscated all of our cats due to a government investigation. First, a beaker of water is brought to its boiling temperature of 1,000 degrees. Then, noodles are added. Let them cook for 8 to 10 minutes, or until the noodles are soft. Macaroni will expand. Then add butter, milk, and processed cheese powder. But first, strain the noodles, because otherwise they will explode. Now, find an airtight box. If you don't have one, a large cabinet or a large rubber duck will do. We'll be using this trash can. Next, prepare a solution of geranium hydroxide. It should be a delicate lavender color, much like the lilac flower. Place it inside the box. Then find a curiously suitable test subject.
Or a pirate. I would have made a grand pirate, sailing the seven seas, wearing eye patches. You know, they didn't actually wear eye patches to not be able to see.
All right, it's been about 30 seconds now.
So as I was saying, pirates, they did actually...
As you can see, our subject has taken the living form. More's the pity.
Before we introduce our final topic, we're going to have to discuss another aspect of quantum mechanics. Now, as we mentioned earlier, the nucleus of every atom is held together with a piece of string. However, not only are they held together with string, but every particle on the fundamental level is in fact composed entirely of one continuous strand of string, much like a spider web or the human brain.
For example, this is what a hydrogen atom looks like. Here is a skin cell, and here is the ever-popular cat's cradle.
Because of quantum uncertainty, string theory, and a desire to make some actual sense at some point, scientists came up with quantum entanglement. Because everything is made of string, it is possible for things to get hopelessly knotted together. When this happens, any change in one is immediately affected in the other as well, no matter how far apart they may be.
This theoretically allows for very effective superconductors, mass production of nanochips on the atomic scale, and perhaps the greatest gift quantum mechanics has given to humankind: the quantum eraser.
Quantum erasing is really quite a simple process.
First, you must hopelessly entangle the subject with your particle.
Perhaps being a tree would be fun. I mean, sure, it's a sedentary lifestyle, but, you know, photosynthesis isn't the worst thing you can do with your time.
Then, destroy the particle. The object has now completely disappeared. You may have seen this at work at your local landfill destroying garbage. It's also a traceless method of offing someone. Well, that's it for quantum mechanics. Please join us next week for the effect of the banana on Elizabethan playwrights. Until then, as always, look around you.